can try to find the solution, and then we can solve it on the blackboard. As you remember, in the first lecture, I told you that the sensitivity for a double beta decay experiment is defined by one of these two formulas. The first one is the one that is used in the case of non-zero background. That means when you expect to see a number of statistically high number of counts in the energy region of interest. And the parameters are the mass of the source. I mean, it's a number that is proportional to the number of double beta decay candidates, the number of isotope that you have in your source. We assume to have a source that is itself the detector of the decay, and T is the exposure, therefore the amount of time during which I count events. B is the background index, therefore the counting rate, the number of counts per kV, the counting rate normalized to the energy window. Therefore, the unit is usually counts per kV per kilogram per year. And then delta E is the energy resolution of the detector, but in our case is exactly the width of the region of interest. So we have this you remember we have a spectrum. This is the energy, and we have counts. This is a differential spectrum. And this is the region of interest, and the width of this region is delta E. We measure it in keV. Here we count events, and we have a background level B. The units is counts times keV, kilogram per year, though this kilogram is the mass of the source. Okay, I normalized that to the mass of the source, and the mass of the source is a constant times the number of isotopes. Okay? So try to understand why we use this formula. So the idea is, I want to define which is the half-life that corresponds to the minimum detectable number of events over background. Is the question clear to you? I mean, what is the problem that we want to solve? Assume that I have my experiment, and I know which will be the counting rate in the region of interest, because, for example, I have a background model like the background model that I've shown you. I already have a background model similar to the one that I've shown you, that of Quare, but I have also background prediction for Cupid. So I know, more or less, what will be the counting rate in the region of interest. I know what will be the energy resolution, and therefore the region, the width of the region of interest, because it's the energy resolution of my detectors. And then I know what will be the mass and the exposure of my experiment. So I wonder, because I have to go to my funding agency and tell, okay, my experiment has this cost, I want to be funded, But what I will offer you is that the sensitivity of my experiment will be this one. So I need to be able to predict the sensitivity of the experiment. And so which is the worst condition? The worst condition is that I do not see the peak. Why? Maybe because double beta decay does not exist, or because I do not have events, because I did not wait for a time long enough. And finally, it is also possible that double beta decay events are there, but hidden by the background. Okay? So, my need is to understand what is the longest half-life that I'm able to see with my detector. Okay? Therefore, what I'm going to measure is the number of counts in my experiment, that is B. Remember, this is, we often call it background index, and so the units, it's counts, kV, kilogram here. And so I have to multiply for all these parameters in order to get the number of counts, right? So is B, the energy reserve, my energy interval is this one, the region of interest, its width is delta E, the mass is M, and the time is T. And this is called exposure of my experiment. This is the number of events that I will count, the ground events. And to be able to see my peak, I need at least, which is the smallest peak that I will be able to see here. You see, the peak should be, I've drawn this, these are the statistical fluctuation of the ground. And so my peak needs to be a bit higher. I can, as you know, there is at least in the world of particle physics, we claim a discovery when we have a signal that is 5 sigma outside statistical fluctuation, but it's convention. I can take 1, 2, 3, how many sigma you like. The unit of measurement is sigma, okay? So, my peak should be at least comparable with the statistical fluctuations of the ground. A statistical fluctuation of the ground, if this number is high enough, they are measured by the square root. And you may remember that this is what is called the Gaussian approximation. Okay, that means you need to have n large enough that I can assume that fluctuation they are Poisson fluctuation, but I can approximate my Poisson with the Gaussian, and in that case, my best evaluation of the Gaussian standard deviation is the square root of n. If I have few counts, this approximation does not hold anymore, and I have generally to define an upper bound using Poisson statistic. This is the field where you can either be Bayesian or frequentist, and there are different recipes, but at the end, numbers are not very much different. You know which is the value of this number to be in the approximation, for the approximation to hold? Well, of course, since it is an approximation, there is no number. I mean, it depends on your feeling. Oh.
No worries, no worries.
So, more or less is 10, 3, 10, something like this. You can look at the tables and you can compare what is the exact value of this number for the standard deviation in Poisson statistic compared to the approximate evaluation that you get from the square root of the number of counts. This problem, you know, it arises from the fact that I'm evaluating the standard deviation of the distribution from an experimental measurement. Okay, so in a Poissonian, the expectation value of the standard deviation is the square root of the mean. But this is not the mean, this is a number, my estimation, okay? So, in any case, let's consider the case in which I have a reasonable number of counts here. This is the fluctuation. And then you have just to remember that the rate, this is the way, the rate of a source is the number of candidates divided by the live time. Okay, so we can, if we take tau is the number of candidates divided by the rate. And then I can evaluate the rate that corresponds to my statistical fluctuation. It's the square root of n over time. Okay, so this is so this is the rate corresponding to a signal that is has the same amplitude of a 1 sigma statistical fluctuation. Then what I get, this is proportional to n beta beta is the number of isotopes that I have in my source, is proportional to m. So this is the exposure. And this is the square root of okay? And then what you get is this. This is proportional. Okay? So now assume I do not have counts here. If I do not have counts, I can just take the PDG, the particle data group booklet, and you will find a page where for Poisson statistic defines the upper limits corresponding to 0 counts. And I mean, there are papers and papers that discuss how to set this upper limit, but in any case, the number doesn't change. If I don't remember, it's 2.3 at 90% level, but you have to check because I'm not sure, but I mean, if it is not 2.3, it's 2.6, it doesn't change. And so this time, this rate is 2.3. And so okay. Are you convinced? Okay. So, there are a lot of details. Of course, you need to understand what are the different parameters that really connect the not one to parallel proportionality, but there are a number of parameters over there. And one of them is the efficiency, the detection efficiency, therefore the probability that if the decay take place, you are able to detect it. Therefore, you find a count in your spectrum. Moreover, this is the easy way. There is one additional detail. Now I have considered a single bin, and so I applied all the consideration, statistical consideration are applied to a histogram with a single bin. I could add the shape of the Gaussian and decide to integrate on the whole signal. Okay, but there are details. Okay. So this is the oversimplified solution to find the sensitivity. The alternative, to be more precise, have you any idea what could be the alternative if I want to? When I get my final spectrum, I'm not simply integrating in one bin. I've shown you this morning. You see what I do? I fit my spectrum, I fit the peak, I fit additional peaks, I fit the background, and here the background is flat, nearly flat, or maybe is really flat in this case, but depending on the result, on your experiment, and on the region of interest can be populated by more peaks, or you can have other shapes. And maybe the shape of the peak is not exactly Gaussian. Maybe the response of my detector to a monochromatic line is not exactly Gaussian. Indeed, it's not in the case of Bolometers. So I have to add also that. And therefore, I mean, my simplified evaluation would hold if I just use a large size bin and I reduce the information that I use. I just integrate in one bin and evaluate the sensitivity. The alternative, shall I? The alternative is to rely on Toy Monte Carlo. Okay, so you simulate your spectrum, and there you can simulate a lot of features of the background, shape, on the behavior of your spectrum. Maybe your spectrum is indeed the combination of a lot of detectors, and each detector has its own energy resolution and response. I can put all this information in my simulation and simulate the effect of all of this. And then I can fit the spectrum and evaluate sensitivity. I can run my toy Monte Carlo a lot of time in order to have an average estimate of the sensitivity. So the sensitivity is very useful when I have to ask money, but that's not the end of the story. When you read a paper with the results of a double beta decay measurement, look for the sensitivity. The fair way to show the result is to say the half-life is that one. Okay. And the sensitivity, I don't remember the sensitivity in this case, but in the paper is written. The sensitivity is and do you know why it is important? Which is the difference between my result and my sensitivity.
Well, the way I like to think of it is kind of like the reverse. It's like, assume that double beta decay exists. What is the smallest half-life we could have where we should see a peak, but there is none because of statistical fluctuation? So it's like instead of thinking, how large of a peak do I need to claim discovery, it's like...
No, that is not, is the difference between the sensitivity and the discovery potential. So this is true, again, is the difference between sensitivity and discovery potential is really a technical detail that can be important, especially when you have zero background, but it's not what I want to discuss. So,
the word itself, no? It says that, okay, maybe this is also higher than that, no? But how much higher can you go with this experiment to actually test it before?
so it's the same difference between this and this. The expectation value and the mean. Sorry, no, the expectation value, no, sorry. This is the expectation value. A sample and the expectation value. Okay? That is the difference. So, assume we have a Gaussian. This is mu. And my single sample can be here, quite close to the sensitivity. It can be here or here, okay? So it is important to understand if my value is very high, but very far from the mean. If it's very high and very far from the mean, it is very likely that this is only a statistical fluctuation. No, it's not a number of sigma, because, I mean, this, after the measurement, I only have my sample. And I say, this is my best estimate. Okay, this is what you do when you do not know. And this sensitivity is, I mean, the best you can do with but it's not the physical result. The physical result is the sample, okay? So if you do a measurement and you only sample once your PDF, that is your best evaluation of the result. However, if the sensitivity tells you that probably you are in the, I mean, is a statistical fluctuation, probably because, of course, the sensitivity is an approximate evaluation of your expectation, because it is based on simplified model. Toy Monte Carlo is, in any case, a simplified model. So you are not going to provide the sensitivity is not the result, okay? However, if it is, your result is very far from the sensitivity, yes, you may assume that on one case, I mean, it is, if it is, you get a short half-life, it may be because you have a signal in there, okay? If it is a very long half-life, it's not, you have an under-fluctuation of the background. Okay, so of course, if you have a short lifetime, there are two possibilities. Either there is a signal in your spectrum, or you simply have a positive fluctuation in the background. On the other hand, if your half-life is very long, is longer than the sensitivity, higher than sensitivity, the only possibility is that either your sensitivity is wrong, or you have an under-fluctuation of the background.
Some kind of distant relative to the p-value concept. Distant.
You mean the p-value in a chi-square? I don't know if I'm happy with this comparison, but let me try to tell you why I'm discussing this point. So this measurement is very long. I collect statistics for a long time. And then I have to decide when I want to, you know, the analysis is generally blinded. Does everyone knows what I mean by blinded analysis? Or do you want me to explain? If somebody does not know, I can explain. Okay, if you know what
I think it's when you have to do the cuts to the data, but you don't have, so you must be careful not to cut the things you don't like because you want to find what you want to find.
Oh, exactly. So you refine all your analysis procedure without being able to know the result. Okay? So, for example, in the case of double beta decay, it's quite easy since your result is obtained by looking at a small energy region in your spectrum. The solution is that this region is blinded. When you draw a histogram, you do not have the possibility of looking in this box. Okay? And so you, define the analysis procedure without being able to to look in this very small energy region, especially for, in the case of high resolution detectors, it's quite easy because the energy region is a few kV, so that's it. Then I have to decide when to open the box and publish results. So I can fix a date and say, okay, I publish it. However, one possibility for biasing, even if it is not exactly a bias, is that every month I look in my box, I open my box. When I see an under fluctuation, I publish. Or when I see an over fluctuation, as you prefer. When do I have to publish if I want to have a very good limit? When I have an under fluctuation, my limit goes up. And if in my paper I forget to add the sensitivity, maybe the under fluctuation is not that clear. And for a while, in all this plot that I've shown you, my point is the best one. So be careful when you read papers. No, it's perfectly allowed. I mean, there is nothing, you're not biasing the analysis, you are biasing the publication of the paper. No, it happens. Of course, it's not written in the paper, but I mean, you can suspect that it happens. So for sure, nobody told me. No, somebody told me also. But in any case, it's not a... No, there is no error bar. It's an upper limit. There is no error bar. It's an upper limit. The only way to understand if it is a fluctuation is a comparison with the sensitivity. So in some way, the error bar should come from the comparison with the sensitivity. But if I don't add the sensitivity, or in any case, maybe the sensitivity is there, but in any case, when your result is reported, is the result that is reported, not the sensitivity. And often, as in my case, if you look at in my slide, I forgot to add the sensitivity even for the Cuore result. Of course, it's not sharing. Okay, so I forgot, and it happens. In that case, as you see, there is not an under fluctuation.
But that should be good practice. Always comment.
Yes, yes, indeed. But sometimes people forget good practice. I mean, it's the referee that should ask to add this information, okay? The peer review is intended also to guarantee that all the information are there in order to be able to judge the paper. Okay, so that's just to highlight that sometimes even when you read paper, you have to be careful, and of course there are strategies. I mean, maybe if my result is very good, I get the funds for the next generation. I don't know. In this case, I mean, I know somebody that has done something like this, but I don't think it was for this purpose. But maybe to be the best result in the plot that generally we show, yes. And you remain there for a while, you understand? Okay, so let's change topic. And let me come back to this plot. You remember this plot from this morning? So the black histogram is the physics spectrum, and This vertical scale refers to the counting rate of the physics spectrum. The red histogram is the result of a calibration. It's simply, I mean, I normalized the red histogram in order to have the 2.6 MeV peaks with the same height. And my question is, what kind of process is populating this energy region? Look at just at the red histogram. What kind of processes are this? Are the events that populate this region? And this is the information that I provide you. They come from the knoll, and if you open the knoll somewhere, you see that there is this plot that illustrates the spectrum recorded by a detector when is illuminated by a gamma source with a monochromatic line. So there is a photopeak, and then you have the Compton, and we have something that is called the Compton edge. And this is the Compton, the value of the Compton edge. Okay. And so my question is, why I do not see this important, I mean, this region with very almost negligible amount of counts, and why in my spectrum it is populated. Let me go back to the spectrum. Why do I have counts here? Keep in mind the Compton edge is here. Okay? And here I have a lot of events, and also I have a peak here. Can you guess why? No, it's not pylon. The photon, yes, more or less it's like this. So it's losing a part of its energy outside the detector, and then enters the detector once more. So this is called multi-Compton. Okay? I think I also tried to draw it, but I don't remember if it is not here. So it's something like this. In one case, you have a Compton, therefore the photon interacts in the crystal and then is scattered back, and you just have some event in here. Otherwise, you could have a Compton here, and then the photon is scattered toward the crystal. Here you have some energy that is transmitted to an electron inside this material that could be the copper holder. You lose a fraction of the energy, and then the Comptons and the photon enters here, interact 2-3 times, and then is absorbed with a photoelectric. All the energy is deposited, and so you get something that is in here. So there are only few keV that are lost in here. So you see also which is the solution to remove all this event here. You should avoid to have material where the energy, inert material where the energy can be released. And so you need in some way that everything surrounding your detector is active. That's not easy, at least for bolometers, but that's it. And then the other peak. You know what is this? What is this peak? It's a very, very small peak. Is an escape, is a X-ray escape due to excitations produced by the thallium photon. So the thallium photon excites the tellurium, and then you have a X-ray escape. Okay. Something that I've not shown you so far is a scatter plot. So let me explain you how it is drawn. When you have an array of detector, here you see a 4-crystal array. I told you we operate each detector independently one from the other. So they have their own electronic readout chain. Generally, now I digitize the output, and all the analysis is done offline. So I can draw two plot like this that show how the voltage here is already calibrated in energy, but I mean the energy is the pulse height, not exactly the the amplitude of the pulse, not the vertical coordinate. In any case, I mean I can see the evolution of the voltage during time on the two crystals. And you see pulses, and I can also define coincidences when the pulses are, I mean, of course, their distance in time is, I mean, is contained inside what I call the coincidence window. So the two signals that I've shown you in the box are in coincidence, while the other two are not, because the coincidence, they are not in the same coincidence window. So these two are not considered in coincidence. These two are in prompt coincidence. So I can plot the energy of recorded in one crystal versus the energy recorded in the other crystal. And for each coincidence, I will draw a point in this plot. Okay? And I can do this for all the pair of crystals in Cuore, Cuoricino, or whatever array. And I get this plot. And you see in this plot, I have lines, diagonal lines here and here, and then I have vertical lines. Can you guess what are the processes that produce these lines? We have two families of gamma lines. This, they sum at an energy that is between 4 and 6 MeV. And this is a spectrum without any source, so is the spectrum physical data, okay? So what I call a background spectrum, so only events that are due to radioactivity or muons or neutrons or whatever. So these are alphas. These are monochromatic. Alphas have a monochromatic emission, so they are the alphas from the uranium and thorium chain, while these other lines are the gamma lines of the same chains, but these are gamma lines because there does not exist alpha, not in the uranium and thorium chain at these energies. Okay, and which is the process that produced this line. It's Compton. Okay, is Compton, and this lines. Okay, this line, the position is the same as this peak, is the 2.6 MeV. However, I have a vertical line. And there are more than one explanation for that. Exactly. Yes, exactly. Indeed, I think I have. But there is also an additional mechanism. No, this one. So, I don't know if you can see here, the 2.6 MeV event is this, is the first excited level, the emission to the first excited level, and then the following level at higher energy has an emission at 583 keV, and they are, both of them are prompt gamma rays. So when the decay populates this high energy state, I have two gammas, and they can sum in my detector, but one of them can also undergo Compton in an inert material, so some energy is lost. So in that case, I can have the minimum energy is one of the two gammas, the maximum energy is the sum of the two gammas, and I can have events in between because one of the two or both the two can lose some energy outside my detector. The other can see one of the, yes, exactly. And that at the end, in that case, you have the maximum energy is the sum of these two. And then if, I mean, the contamination is close enough to my detector that also the beta enters the detector, of course, I can have also beta. So I have a lot of possible, I think this is, I have a lot of possible different combinations that can produce that line. And if the rate is high enough, I can also have accidental coincidences in that case that can provide contributions. Yes. Sorry. Yes, accidental means. No, I was wondering why you were explaining what is accidental. Yes, accidental. No. Okay. Yes, accidental means that they do not have a real correlation, physical correlation, as when they are produced in a decay of a single isotope or in the decay chain of an isotope, but are due simply to the superposition of events that, due to high rate, can accidentally occur. Therefore, the probability is just the product of the two rates and the width of the window.
That can get better if you reduce the range in which you consider.
Yes, exactly. Indeed, if you want to measure only the accidental coincidences, only if you want to remove the accidental coincidences, you try to reduce the window. And okay, I don't like this. And the other possibility that we use in Cuore is that sometimes we define coincidences with a time window and also a maximum distance among the crystals that can produce a coincidence. So you have a less number of crystals, therefore, the total rate, if you want, is reduced, and you can use, you have less accidental coincidences. And so to show you, I think I also tried just to go a bit deeper. And then let me show exactly what happens when you have bulk on surface contamination that produce a coincidence. I have used this different representation of alpha plus recoil. And so if I have a decay that is fully contained in the bulk of the volume where it takes place, if it is in the crystal, I see a line, and the energy corresponds to the Q value of the transition. So my example here rely on polonium 210 decay. Is it alpha decay? Value, let me remember. So yes, Q value is, I think is this one. The alpha is and the recoil N, okay, is are the energies, okay? So you see this event in crystal 1 produce a count in correspondence of the Q value. This in the copper, or outside, just outside the copper, does not produce any event count in my spectra. This one on the very surface of the copper, just assume a polonium atom that sticks on the surface. Since I assume here that the topology is the alpha goes in the direction of the crystal and the recoil in the direction of the copper, produces a peak at the alpha energy, a count at the alpha energy. So when I look in the crystal, I will see a peak at this energy for bulk contamination of the crystal, and a peak at this energy in the case where the contamination is on the surface of the copper. When the contamination is on the surface of the crystal and I have a coincidence, I have one count here and one count here. I record also the recoil. And what I mean by very surface contamination, I mean something, this I know from Monte Carlo simulation, something where is maximum in 110 nanometers deep inside the surface. Okay? If I have a contamination that is a bit deeper inside the surface, say 10 micron, then a fraction of the alpha energy is lost in the source crystal and sums to the recoil. So I see a recoil that has a higher energy than the recoil energy. And I see also an event in the nearby crystal that is at much smaller, lower energy than the alpha energy. And the same takes place in the case of copper. Again, the alpha can lose a fraction of its energy in the inert material and then enters the crystal with, say, free MeV energy. So what happens? This event this kind of events produce this diagonal line. Those that are due to a deep contamination, deep surface contamination, produce events that populate the central part of this plot, while when the contamination is on the very surface, I produce event here. Therefore, recoil on one side and alpha particle on the other. An event that described here as deep in the copper source, in the copper surface, does not produce events in this scatter plot, but produce events in here. So this flat background is due to, in part, a fraction of it is produced by this kind of event, deep contamination, deep surface contamination on crystals. But most of these events are removed if I only accept what I call multiplicity one events. So events where only one crystal is firing. No other crystal, in my coincidence window, I only have one crystal firing. So this can be removed. They populate this region, but I can remove them. While this populate this region, and they are my problem. And the only solution for this, unless I remove completely all the inert materials, is to clean very well this surface. Okay, and that's it. These were the only few exercises that I've tried to prepare.
Sorry, on the example, the previous example, can you please show the previous? Okay, yes, this one. So this produces a point, right?
Yeah, this
example here.
Okay, these two events does not produce.
No. The fact that the alpha crosses the crystal one.
This.
And the recoil stays in crystal two.
Yes, they produce this. One point in the scatter plot and two events, one for each crystal.
Okay.
So this event produces in crystal 2 this event, the red event that is the nuclear recoil. And in crystal 1, this event that is the alpha energy. And when I combine the coincidence in my scatter plot, I get a point that is quite close to the axis.
Yeah, exactly. Okay.
Is either here or here in.
Okay, I wanted to make sure.
Okay. So that's it. Do you have any kind of question or curiosity also on the other topic that I presented you?
Well, since we have time, there was something I was a bit curious about. It's maybe a little technical. couple days ago that molybdenum is kind of a neutron magnet to a certain degree, right? So it tends to capture neutrons, or am I misremembering?
No, okay, I have a few slides on Roman lead and I can show you, and then we can go deeper if you want to. So let me. Okay, so this is the Roman lead. It was found in the Sardinia Sea, and we had to cast this lead to prepare our shields. And so you may wonder why we need this lead surrounding the crystal, and what is the advantage of using a Roman lead? Can you guess? No. Most of people is convinced that the reason is because it was underwater. No, because it is true that water can shield, but the problem is that lead is not activated. And then, in any case, lead comes from an ore and a mine, and so it was already shielded. So you don't really have a gain from that point of view. Because Romans were able to, more or less. More or less, it was spatial lead. So let's start from my need is only to have a very clean lead, okay? Because, no, there are, not all the lead are, from the point of view of mechanics, they are not identical among each other, but that's a different story. So my need is to use lead, simply because it has a very high density, so it's a very efficient shield. And since I want to place it very close to the detector, it has to be very, very clean from the point of view of radio purity. And then lead is not activated by neutrons. I mean, everything can be activated, but it's not relevant. So there is some radioactivity that is not in Roman lead and is in all the other lead. Not in all the other lead, but because?
The radioactivity isotope of the lead already passed along.
Yes, but what is the radioactivity that is removed? It's lead 210. Okay, when you buy lead, you can purify it. It's very easy because, you can cast lead, it becomes liquid at very low temperature compared with other metals. You can even probably do it in your kitchen, but don't do it. And this is a good way to remove impurities. Because metals tend to crystallize after they are melt, and crystallization is a good way to remove impurities in general. So when the Roman purified this lead, but I can do it even now. Maybe Roman were very smart, but I think we can do something similar. Okay, we have the technology, we have electrical power, so we have some advantages. Okay, so we can do the same. Therefore, this is not the real motivation. So the difference is just that they have done this 2,000 years ago. And why that is the difference? Because there is only one radioactive isotope that no way I can remove from the lead, and it is lead. Lead 210 is a radioactive isotope, and I cannot remove from lead because, I mean, I need isotopic separation to remove lead 210 from the other kind of LEDs, isotope of LEDs. And so it's not possible. So my problem is lead 210. If I remove uranium and thorium, I do not remove lead 210. And also Roman did not remove lead 210 for sure. But lead 210, you can see there, has a half-life of 22 years. So if, assume I fully remove uranium and thorium, and they are long-lived isotope, but all of them are different from lead. They are radium, thorium, uranium, and when I melt, when the Roman purified the lead, they really removed all the impurities. So they had pure lead with lead 210. But 22 years is, it's a short time compared to 2,000 years. The Notre Dame roof there is a lot of lead and is ancient enough to be used for the next experiment. So. Yes, the lead somewhere should the lead will be still there. It's old. If they have cleaned it, purified it before using for the roof, maybe we can use it. Okay, in any case, lead 210 now is completely decayed. So in the ancient Roman lead, if really they removed completely uranium and thorium, lead 210 is not more present. And indeed, we are not able to measure it. The only way in which we were able to measure the content of lead 210 in Roman lead was to melt a small amount of lead. We did not exactly grow a crystal, but we obtained a crystal. And then we operated it as a bolometer. It didn't work very well, but we were able to measure the contamination of this of lead 210 that was of this level. Okay? And we are able with other techniques only to measure contaminants. Lead concentration, lead 210 concentration that is order of magnitude higher. We do not have sensitivity. There are no gamma rays emitted that only at 46 kV. That is very, very low. So the idea of using lead is simply that the lead was purified in ancient time, and therefore, once all the uranium was removed, the chain that produced lead 210 was no more fed, and therefore we do not have lead 210. And now we have still a problem. If you look to the Q value of all these isotopes, none of them but this alpha particle is above the double beta decay transition energy of tellurium. So there is no motivation to use lead 210, to be afraid of lead 210. Moreover, you see, there are no gamma rays, there is, in this, this. Okay, you have two branching in the decay of lead 210. This is a very low branching rate, branching ratio, so just look to this decay chain. Lead decays is a beta decay with the emission of a line at, I'm not able to read, but somewhere is 46 kV. And then you have bismuth 210 that again, beta decays without gamma emission. So why I'm worried? The first decay, lead 210, has a very low Q value, so forget it. Bismuth has a Q value of 1 MeV. It is a pure, maybe it's not completely pure, but almost pure beta decay. Keep in mind that if I buy standard lead, the contamination is as high as 100 becquerel per kilogram. So it's a very high rate. So what happens in my lead when I have a decay, a beta emission of 1 MeV? I mean, 1 MeV, the range of an electron of 1 MeV is nothing. My lead shield is a few centimeters thick, so I stop it. Then, why? What happens when I have a MeV electron that... Sorry? Into pair, no. Sorry? Not X-rays. Why X-rays? It's a charged particle that is stopped in material. What happens when you stop a... Bremsstrahlung. Okay, so there is a lot of Bremsstrahlung. And so it's not a problem that this event populate directly the double beta decay region. But they produce a huge rate in my detector. And so this is a problem because I can have pile-up, it can increase the temperature of my detector, but it's not only a problem of bolometers. For example, when we were able to use this lead, we were asked by a lot of collaboration to have a smaller amount of this ancient Roman lead to shield the germanium detectors from the readout electronics. If you want to place, if you have the electronics, electronics is always made with material that is highly radioactive. And so you need to shield the detector. The best is to have a very thin foil of lead, but you do not want to use a normal lead. And then, just for your curiosity, lead, I mean, the content of lead 210 in the lead that you can buy on the market is very different from kind to kind, and it depends on the mine. So some years ago, it was available a kind of lead. It was produced, at least sold in Poland. I don't know if it was produced there. That was very clean. That means the radioactivity was 5 becquerel per kilogram. But then the mine was closed because probably it was not more producing lead. And so now the radioactivity of the commercial lead is a bit higher. And in any case, in Cuore, we decided to use Roman lead in the vessel that surrounds the crystals, but not on the top. Okay, because on the top we have this, we have thick copper plates that shield our detector from the modern lead. If you want to shield Bremsstrahlung, you do not need that much thickness, and so this copper is enough, and so we used the Roman lead only on the side and on the bottom. And then from the point of view of the content of uranium and thorium, it's hard to say if modern lead is better or it looks a bit contaminated more than the Roman lead. The problem is that we are not able to measure it with germanium. It's beyond our sensitivity, so we can only use the background model of Cuore to infer the contamination in the different shields. So this is the story of the solution. And the motivation why we did not use copper, because at the end copper is, the density is slightly lower than that of lead, but the uranium and thorium contamination are probably better. And because copper is, since you produce it for the electrical properties, you need to have a very clean copper. And so when you remove impurities that compromise the conductivity, you also clean from most of the impurities. But the problem is what I've mentioned you before, that is the transition, the possibility that you have hydrogen inside the copper. And if you have hydrogen, you can have this latent heat that due to the transition from ortho to para hydrogen. And this is a bit worrisome. It was worrying us, and so we were not convinced of using but maybe for Cupid in future we will consider this possibility. I have no idea. I can tell you the story. I think that there was a lot of confusion, and I realized once I was invited say 15 years ago in Mexico. It was a workshop organized by nuclear physicists, and they asked me to give a review on double beta decay experiment. They really did not have any idea of what double beta decay was, because you have to know that now the community of nuclear physicists that are working in the field of double beta decay, providing computation of the nuclear matrix elements, is a bit bigger than it was in the past. So they had really no idea, and it was completely a chance that they invited me. The place was wonderful, I must say. In any case, I gave my talk, and that's it. And then we had lunch together, and they have no idea of Gran Sasso, of underground experiment, but everybody did know of Roman lead. And they, at the end, they really were more interested in the story of Roman lead than in that of double beta decay. And all of them were convinced that the problem was that it was underwater. So I don't know, I think it was a misunderstanding that somebody was telling the story, and of course it was underwater, that is true, but this is not the reason why we use it. Simply there was a lot of lead in and the Notre Dame roof was not viable, and I think even now it is not viable. So no, we did not ask. Also, but I mean, for us, the Roman lead is enough now. So tons. This was, the expedition to get all the Roman lead was paid by INFN, but 30 years ago. And then only a small amount was given to our group and to Gran Sasso, and we stored it in Gran Sasso. And then when we decided to build quarry, because at the beginning we just used a small amount for a small shielding, so that was used in the other cryostat, in the smaller cryostat. Then, but all the lead was somewhere in Sardinia. It was not in exhibitions, for sure. No, there was some of these bricks were you could see down in the floor in the Cagliari Museum, Archaeological Museum, but with no indication of what it was. But in the basement of some museum, there was this huge amount of Roman lead, and we asked to use it for quarry, and it was incredible that we were allowed. We had to remove this inscription. There are 4 different inscriptions on the bricks, depending on the brand. Okay, and so one is Famiglia Pontigliena or something like this. It was in my picture, but there are 4 different. We had to remove all of them. They are in Gran Sasso in the exhibition there. And all the other part we had to remove all the residuals from the sea, and then we melt and produce the shields. But the shields, I don't remember, this shielding is more than 1 ton. Okay? Any other question? Yeah. Okay, so okay, the answer is that not all this information are directly available, because you can rely on simulations, but simulations depends on a lot of parameters that are not easily measured for the real configuration of your crystal. What we know is that when you have a crystal, you have this hot spot where you deposit the energy, and you produce first these high energy phonons, and you can simulate them, and they travel through the crystal, they move, they are the processes that degrade their energy in order to lead to thermalization are scattering on impurities. Also, there is also the isotopic scattering. So when you have a different isotope, you have a degradation of the energy, because I assume the periodic potential changes a bit, and then reflection on the side of the crystal. So if as we do for quarry, you have a glue here, and then the sensor. What we know, from simulation, measurement, and so on, is that only thermal phonons are able to cross this interface. And therefore, the signal development takes place once we had the thermalization here, or nearly thermalization. In any case, all the diffusion is done. If you use a TS or something like that, so you just have a film here, and it is possible that you are sensitive to high energy phonons. Therefore, in some way, you are sensitive to the diffusion. There is non-equilibrium, and what you may see, and then in this case it depends on the material, on the size of the absorber, on the size of the test, on the interface, and so on. What you may see is a sensitivity to the position where the event, I mean, the position where the energy have been deposited. And you see this because with a monochromatic energy reposition, you see pulses with different height. So this is the proof that in some way you are sensitive to the only way in which we understand that we are seeing a signal that is produced not in thermal equilibrium is that this signal is sensitive to position. So it's not only thermal that you are not in thermal equilibrium, but you are not uniform. We want, depends, yes, of course. This means that, for example, you can have a very, very fast signal, but you lose in energy resolution. So whenever you need energy resolution, you want to avoid it. For example, when I discussed this morning the problem of pile-up in our detectors due to the 2 neutrino double beta decay, in principle, what I could consider, it's not feasible, but for several reasons, but I could add a TS here and have, this is my NTD germanium thermistor, have a slow signal, thermal signal here, and here I measure the energy. And the fast signal here is just to see if I have a pile-up. So in that case, the two, I'm able to see separately the two events, and it doesn't matter if I'm able to measure their energy. However, you need to be able to have, to deposit the film on this crystal and see and generally what happens is that you are sensitive to the position when you have small detectors. But that's more or less, and this behavior really depends on the detector and on the sensor. And to avoid this, what is done also in microcalorimeters, you know, they are used to study the beta spectrum of some isotope. Maybe it's not a beta, but because from the endpoint you can measure the neutrino mass, like in Catherine. And so you need a sensor with a very high energy resolution because you generally choose a low energy isotope. So, an isotope with a low energy Q value so that you are sensitive, you have a better sensitivity in measuring this gap. I mean, the distance between the nominal endpoint of the isotope and the neutrino mass. So you want to have a very good energy resolution, and you want a very fast detector because you need to avoid pile-up also in this case. And since you need to have a lot of events, you are only I mean, all your information are in the endpoint, so you need a source with a lot of, that produces a lot of event there, otherwise you are limited by the statistics. So the compromise is to use, for example, a TS, and then you use, I mean, you have a beta source, and often you have something in between in order to avoid the transmission of not thermalized phonons, or in any case to avoid this dependence on the position. And the same is true also for the Maura experiment that is using the lithium, the same crystal that we plan to use for Cupid, but a different detector, a different sensor that is a magnetic metallization detector, MMC. And again, what they do is to put here some gold, and then they have a connection to the sensor. So here you have a sensor. The gold collects all the phonons, and then you have a thermal transmission to the sensor. In this way, you avoid any dependence on the phos signal. So in the past, when I was of your age, we discussed a lot also crystals that have anisotropic let's say, where you expect that phonon diffusion is anisotropic. Because you could develop, in that case, a bolometer sensitive to the direction of the particle. And that was, I mean, the idea was to be able to measure the direction of the nuclear recoil induced by weakling interacting particles. But it's completely impossible. It was really, I mean, for simulation only, not for real detectors. Because all this, I mean, there are a lot of properties that in the reality cannot be observed because you are never playing with really an ideal crystal with a perfect lattice without any kind of defect, and defects means either impurity or defect in the lattice. So you should have for all these phonon properties really a perfect lattice with all the atoms placed exactly in the whole crystal exactly in the same position. And it's not something that can be achieved. Other questions? Okay. I think Florence is there and you can go.